Okay, so today we are starting free energy and equilibrium. So we have delta G, and we are bringing in our favorite big K. So with temperature, the magnitude of H and S don't change very much. It's very small. So what we can do is we can say that delta G, free energy, is equal to the change in free energy at standard conditions plus the R, which is, we have several R's. You're using 8.31 joules per mole. We're not using the latums. Times the natural log of Q. And what is Q? He is wannabe K. He is special K, so non-equilibrium constant or quotient. No, it was the K we did back in equilibrium. Remember, K is products over reactants. All right. Delta G, I just told you guys what all those things stood for. If the system is at equilibrium, so if we are at equilibrium, K equals what at equilibrium? Anybody remember? K equals 1. At equilibrium, then delta G is equal to 0. If K is less than 1, which means if you have your products over your reactants are the ones that are being favored, then delta G is positive. If K is greater than 1, this time your products are being favored, then delta G is negative. So if I give you a delta G and it's negative, you can tell me which one's being favored. Okay? If I give you a K and it's less than 1, then you can tell me that whether the delta G is spontaneous or not by looking at the K. Okay? So if you're at equilibrium, so if we have this, all right, and we're at equilibrium, which means that delta G is 0. At equilibrium, ln of K, ln of 1 is what? 0. So we can say that delta G is equal to 0 if we are at equilibrium. So we put this into equation, rearrange that equation to get rid of that 0, and we can say that delta G is equal to negative RT ln K. Yes? Okay, so negative RT ln K, and that I just say is negative rat link. Okay, so you have the equation, but I say it's negative rat link. So now we have 3 ways to find delta G. We can find delta G using Big Mama. You can find delta G using the ghetto homies, the delta G minus T delta, or delta H minus T delta S, or you can use negative rat link to find delta G. So lots of ways to find delta G. Are there any questions over that before I go forward? Remember, you have a quiz tomorrow, group quiz. Okay. So let's work one of these problems. For delta G of the reaction, which is given here, what was determined earlier, but we skipped that problem. So delta G would have been 97.89 kilojoules per mole. for N2O4, and for NO2, it was 51.3 kilojoules per mole. So it wants us to calculate K at 25 degrees Celsius.
But there's different delta G's for each side of the reaction.
Well, you have a delta G for this one and a delta G for that one.
They're different compounds.
Each compound has a delta G.
Like off the chart. Right?
Yeah, off the chart. So we're going to go find delta G of formation first. So each one has its delta G, and then we're going to find delta G naught is equal to products minus reactants. So 2 times 51.3. If you don't have a calculator, then you need to get one out. Minus our reactants, which is 1 times 97.89. And my G of formation ends up being 4.73. 4.71 kilojoules per mole. Is everybody okay with that? So I just went to the chart, got my G's for each value, and then we got our delta G naught for the reaction. Yes?
If they don't give us the temperature, do we always assume that it's at 25 degrees Celsius?
Calculate. I would say if you see that knot right there, that's telling you that the delta G and that little knot right there, that tells you that standard conditions, which is 298 or 25 degrees.
So on our homework, would we have used them?
Yeah. I'll have to go back and look at it. Okay. So now it wants us to find K, which is our equilibrium constant. So we're going to say delta G naught is equal to negative rat link delta G. Let's just do this real quick. We have negative R is 8.31 joules per mole K. That means my delta G has to be in joules per mole K. So it should be 4,710 joules per mole. Times our temperature, which is 298, ln of K. So get me what ln of K is equal to. Okay, yep. Negative 1.9 is ln of K. So to solve for K, we take e to the power of whatever we have, and we end up with K is equal to what? 0.149? Okay. And the units are what? Oh, it's K. K have any units?
No.
K has no units.
That's why we like K.
That's why we like K. Okay. Any questions? All right, let's go do another one. This time we're going to mess with the equilibrium. So this time, let's change our, we're going to change the pressure. So calculate G for the reaction if the partial pressure is blah, 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 blah. So delta G is equal to delta G naught plus RT ln Q. So I went and grabbed this reaction because we've changed our conditions. We've changed equilibrium.
But there's also
Wait.
a point 1.
It's a point 1.
Wait, where did we
I
get
missed
this
that.
equation?
That was way back here, the very first thing.
And Q is the same thing as K.
Okay, I see it.
Q is the same thing as K, but not at equilibrium. It's found the same way as you would find K.
Okay.
Too many Ks.
Yeah, for real.
Okay, so delta G, what we just found was what? Was delta G naught was 4,720? 10, sorry. Plus R, 8.31. It doesn't matter. T, 298. Ln and Q is products over reactants. So our products is 0.1, but it's 2 of them, so it's squared over 1 to the first power.
Q is products over reactants.
Products over reactants,
In this case,
and the coefficients are the powers. So delta G is what now?
So we're using the atoms for the ATMs for...
Because you can use ATMs or concentration. And we're given constant.
Oh, sorry. Please go over and read about this part.
Because if you go back to the equation, N2O4 is 2NO2. So,
Okay.
so products would be NO2 squared over N2O4.
Negative 6,694.
6,694, and the units would be joules per mole. Not mole K, yeah.
so we would use pressure for Q.
Yes, you either use pressure for Q or concentration.
Whichever one's given.
Yes. All right, so K we found a while ago was 1.15494. What was it? 1.49. And Q is what? 0.1 squared divided by 1 is 0.01. So which way does this shift? Q is less than K. So when we change the pressure, which way do we shift? We shift to the right.
If you want to get to 1.
Because you have K, and then you find Q in relation to K, and which way, ever way it needs to shift to get to K.
Are we finishing this?
It depends on how far we get. All right. The next one, we have this reaction, and it's given us the Kc at 750 K. And we want to know, would you expect this value to increase or decrease at 300 K? And explain your answer using words. No calculations. So the very first thing I would do is, what is K's magnitude compared to 1?
Quite small.
It's quite small, so it's less than 1, right? Now, if I know that K is less than 1, I know what is being favored. Products or reactants? The reactants is being favored, right? Okay, so if I draw an energy diagram, so if we're wanting to favor the reactants, then what would our energy diagram look like? Okay? Because we want to push back, we want to go over the smaller hump. And the smaller hump is on the product side going towards the reactant side.
It's easier to get more reactants than it would be.
Right. Okay, So what type of reaction is this? Endo or exothermic? It's endothermic.
Wait, how's it easier to just do that?
Because do you want to push things up the hill on the left, or you want to go back to push up the big hill or the little hill? Which one's easier?
I get it.
Okay. So it is endothermic. So that means heat is where at on our reaction up above. Reactants or products? If it's endothermic. It's a reactant. So what are we doing? We are decreasing the temperature. All right? So that means we are taking away heat. So if we take away heat, then we are going to push to the right reactants or products. If we take heat away to get back to equilibrium, where do we have to push towards to make heat? We have to push towards the left. All right? So what's going to happen to K when we push to the left? K is going to get what? Smaller. Because we're going to make more reactants at 300. So that's our prediction. We're saying that K is going to get smaller. K is going to be way smaller than what it is right now. Right now, at equilibrium, it's 1.12 times 10 to the minus 3. Once we start taking heat away, then it's going to get even smaller.
Okay. So since heat is being taken away from the reactants, the reaction has to push that way?
Has to push that way to make up for that heat. Yes. All right. So next says calculate delta H and S for the reaction from the thermodynamic values in your text. To save time, so what would we use to find delta H and delta S for the reaction? Big Mama. So delta H for the reaction and delta S for the reaction, we are going to use Big Mama. So I've already done that, and delta H is 114 kilojoules per mole, while delta S is 129 joules per mole K. We are going to need to convert it. Okay, so I'm going to put on here that we use Big Mama. If you need to, you can go and find those. And I'm going to go to the next problem. It says, using the values obtained in B, which we just did, calculate delta G naught for the reaction at 300 K. So delta G is equal to, delta G naught is equal to delta H plus, or not G naught, sorry, that should just be that. Delta H minus T delta S. So H is 114 kilojoules per mole. T is 300, and delta S is 129 joules per mole. You can change it to 0.29, so 0.129 K. So what do you get for delta G? 3 sig figs. 75.3 kilojoules per mole.
What's the difference between delta G and delta G naught?
Delta G naught at standard conditions.
You can have standard conditions and not standard conditions in the same class. This is it. This is it. Right. confused about the other equation
This
now.
the equation for delta G is equal to delta G with standard conditions, and then the RT. Okay.
Just ignore this right here. And that's going to have it on your homework too. So for that one, yeah. All right, so the next one says calculate Kc for the reaction at 300 K. So now we have delta G is equal to negative Ratlink.
Would it be delta G not on this one since it's negative Ratlink?
No. Oh.
Or would it be the delta G?
I'm just leaving it as delta G. Once I start changing temperatures and stuff, I don't really put the knot in there. So we have G is 75,300 joules per mole is equal to negative 8.31 times our temperature, which is 300, and ln K. So ln K ends up being negative 30.19. 30.2. Okay. And then we're going to take the E of that. And K should end up being 7.6 times 10 to the negative 14? 14. At 300 K. So at 700 K, it was 10 to the negative 3. Now we're at 300 K, and it's 10 to the negative 14. So our K got smaller, so our prediction was right. So now we're just going to put it all together. All right, so here we have some information. We have H2O plus Cl2O produces 2 Hocals. Our K at 298 degrees or 298 Kelvin is 0.09. We have the formations, the G, H, and S for Cl2O, and we have it for H2O. So it wants us to find G of the reaction using the above information. So we can say that delta G is equal to negative Ratlink. And I'm using that. You could go in and find some more information and use Big Mama to get where you need to go. But I am using negative Ratlink because we have been given our K. So negative 8.31 times our temperature is 298. And ln of our K, 0.090.
So for this one, we just assume the temperature?
Nope, look up at your K. Your K says K sub 298. So if it would have said K sub 500, we assume it's 500.
Because our K value is dependent on the temperature. That's why we can do that.
Okay, so what did y'all get?
5,963.
5,963 joules per mole. Is everybody okay with that?
How do we know it's joules per mole?
G is always joules per mole. But if you had this, RT is joules per mole K. This is K, and this is nothing over here. So our K's cross out. All right, so tell me, K is less than 1. So that means which way are we shifting? We're favoring the left. All right. So now it says use bond energies to find delta H of the reaction. All right, we've never used bond energies before. But what you need to do is you need to look and see what's being broken and what's being formed. So when we find bond energies, we always look at the bonds being broken minus the sum of the bonds being formed. So if you look at your reaction up above, you have H2O. So you have H2O. So if we break those bonds, how many OH bonds are we breaking? 2, and we're going to say OH, or HO, whichever one you want. So we're breaking those 2 bonds. If you have CLO, so you have O, CL, how many CLO bonds are we breaking? 2. Okay, so my trick is I always put what I'm breaking and forming first before I go find any numbers. And I have the sum of those right there. And then we're going to subtract the sum of what's being formed, and we have an H and an O and a CL. But we have 2 of those. So how many OHs or HO bonds are we forming? 2. And how many OCl bonds are we forming? 2. So now that I've gotten those, I can go get some numbers, or I can look and I can see that I have 2 of these being broken minus 2 of those being formed, 2 of these being broken minus 2 of these being formed. So the overall delta H of the reaction is 0. Does that make sense?
Oh, yes. I have one question from the previous one that I didn't get. Never mind, I didn't get it.
Okay. Everybody's good with this? Bond energy. Okay. All right, let's go to the next one. Find the delta S of the reaction. So we have all that information. So we can go and get delta G. We know that delta G, which we just found, is equal to the delta H of the reaction minus the temperature of the reaction times delta S. And we need to find delta S. So G we said was 59.63. H is 0 minus our temperature, which is 298, delta S.
And so the bond is just another way of the change of
Yeah, and we're going to get really into that in the next unit, or unit after. All right, so what is delta S?
20?
I got negative 20. Negative 20 joules per mole. Everybody good with that? All right, so now it wants us to find the formation, delta H formation, and the S for just Hochul. So we know that for the reaction, the delta S of the H of the reaction is 0. We're going to use Big Mama. Hochul, we do not know. We know we have 2 Hochuls, and that's our X. Minus what we have up at the top for water and Cl2O. So 242, negative 242, plus 80.3. And I find that the delta H for Hochul is negative 81 kilojoules per mole. Somebody second that? Okay. Now it wants us to find the S for Hochul. We know the overall for the reaction is negative 20 joules per mole K. Again, we have 2X, so we're using Big Mama, products minus reactants, and we have 189 minus 266.1. And I get, oh, plus, yes, sorry, thank you. 218. Yeah. 218 joules per mole.
So is this stuff in the chart? Are we finding stuff that would be in the chart?
No, it's up at the very top where it says number 13 for Cl2O, H2O. So for question D, we use what was at the top underneath question 13, that information there, and then the 2 answers we found in B and C to find the answer to D. Okay? All right, so last one. So it wants to find our K at 300. So I kind of messed this one up on the last class, so let's see if I can get it right this time. So K at 300. So this is delta G is equal to delta H minus T delta S. Wait, what did you say? Hold on.
Or is it still for just Hochul? Like,
G from A. Let's do it this way and then see what we get with the next, if we do it that way.
Why can't we use Rattling?
Okay, so delta G equals negative rat link. So delta G, that's what we're looking for. Negative 8.31. Temperature is 300. And, yeah, we can't use K. Because we're looking for K. But we know G when it's at 298, but we're not at 298, we're at 300. So that's why we use ghetto homies first. So I'm going to leave that there because we're going to come back to that. But let's go to ghetto homies. So our delta H was 0. Our delta G was 5963. Minus our temperature, which is 300. And our delta S, which is negative 20. Yeah, that's so funny. No, it's not. That's G we're looking for. Da 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 da. That was what we found in B.
So why are we looking for G?
We found delta G when we had 300 at 298. Now we need to find delta G at 300.
Oh, yeah.
All right, so now what do we get? Sorry. 6,000? 6,000 joules per mole. Now we plug that in RETLink. And solve for K. 6,000 joules or kilojoules? Zero point what? 898. And in units is what? Nothing. Okay, so compare this back to what it is at 298 Kelvin. At number 13 at the very top. So it's a little bit less. So the temperature didn't affect it very much, did it? Because we only increased the temperature by 2 degrees. So, are there any questions over that? All right, your homework is C tonight.